Okay, so hi, I'm Scott Aaronson. I'm a computer science professor at University of Texas at Austin, and my main interest is the capabilities and limits of quantum computers, and more broadly, what computer science and physics have to tell each other. And I got interested in it, I guess, because it was hard not to be, because you know, as a teenager, it just seemed clear to me that the universe is a giant video game and it just obeys certain rules. And so if I really wanted to understand the universe, you know, maybe I could ignore the details of physics and just think about computation. But then with the birth of quantum computing and the dramatic discoveries in the mid-1990s, like Shor's algorithm for factoring huge numbers, it became clear that physics actually changes the basic rules of computation. So that was something that I felt like I had to understand. And 20-odd years later, we're still trying to understand it. And we may also be able to build some devices that can outperform classical computers, you know, namely quantum computers, and use them to do some interesting things. But to me, that's really just icing on the cake. Really, I just want to understand how things fit together. Well, to tell you the truth, when I first heard about quantum computing, I think from reading some popular article in the mid-90s about Shor's algorithm, which had only recently been discovered, you know, my first reaction was, this sounds like obvious hogwash. You know, this sounds like some physicists who just do not understand the first thing about computation. And they're just, you know, inventing some physics proposal that sounds like it just tries every possible solution in parallel. But, you know, none of these things are going to scale, right? And in computer science, you know, there's been decades of experience of that, of people saying, well, why don't you build a computer, you know, using a bunch of mirrors, or using soap bubbles, or using folding proteins, right? And there's all kinds of ideas that on paper look like they could, you know, evaluate an exponential number of solutions in only a linear amount of time. But they're always kind of idealizing something, right? So it's always, when you examine them carefully enough, you find that the amount of energy, or, you know, scales blows up on you exponentially, or the precision with which you would need to measure, you know, becomes exponentially precise, right? So something becomes totally unrealistic. And I thought the same must be true of quantum computing. But, you know, in order to be sure, I had to read something about it. So I, while I was working over summer at Bell Labs, doing work that had nothing to do with quantum computing, my boss was nice enough to let me spend some time learning about, reading up on the basics of quantum computing. And that was really a revelation for me, because I discovered, you know, quantum mechanics is this real thing. It is a thing of comparable enormity to the, you know, the basic principles of computation. You could say, you know, the principles of Turing. And, you know, it is exactly the kind of thing that could modify some of those principles. But the biggest surprise of all, I think, was that I, despite not being a physicist, you know, not you know, having any skill at partial differential equations or the other tools of the physicist, that I could actually understand something about quantum mechanics. So I like to say that quantum mechanics is much, much simpler than most people imagine it could be after you take the physics out of it. It's a certain generalization of the rules of probability. And ultimately, you know, to learn the basic rules of how a quantum computer would work and start thinking about, you know, what they would be good for, quantum algorithms and things like that, it's enough to be conversant with vectors and matrices, right? So you need to know a little bit of math, but not that much, right? You need to be able to know linear algebra, okay, and that's about it. And I feel like this is a kind of a secret that gets buried in almost all the popular articles. They make it sound like quantum mechanics is just this endless profusion of counterintuitive things, right? That it's particles can be in two places at once, and a cat can be both dead and alive until you look at it, and then, why is that not just a fancy way of saying, well, either the cat's alive or dead, and you don't know which one until you look? Well, they never quite explain that part, right? And particles can have spooky action at a distance and affect each other, instantaneously, and particles can tunnel through walls. It all sounds like hopelessly obscure, and there's no hope for anyone who's not a PhD in physics to understand any of it. But the truth of the matter is, there's this one counterintuitive hump that you have to get over, which is this certain change to or generalization of the rules of probability. And once you've gotten that, then all the other things are just different ways of talking about or different manifestations of that one change, right? And a quantum computer in particular is just a computer that tries to take advantage of this one change to the rules of probability that the physicists discovered in the 1920s was needed to account for our world. And so that was really a revelation for me that, wow, even, mere computer scientists or math people who are not physicists can actually learn this and start contributing to it.
Excellent.
Yeah.
So it's interesting, often when you try and pursue an idea, the practical gets in the way.
Yes.
Have you noticed that, some people try and get to the ideal without actually considering the practical, and, they think like enemies? Is it like that you should be letting the ideal be the enemy of the practical?
Well, I think that, there's from the very beginning, it was clear that there is a theoretical branch of quantum computing, which is where you just assume you have as many of these quantum bits, qubits, as you could possibly need, and they're perfect. They stay perfectly isolated from their environment, and you can do, whatever local operations on them you might like. And then, you just study, well, how many operations would you need to factor a number or, solve some other problem of practical importance. And, and the theoretical branch is really, the branch where I started out in this field and where I've mostly been ever since. And then there's the practical branch, which asks, well, what will it take to actually build a device that instantiates this theory, right? Where we have to have qubits, that are actually the energy levels of an electron or the spin states of an atomic nucleus, or otherwise somehow, instantiated in the physical world. And, they will be noisy, they will be interacting with their environment. We will have to take heroic efforts to keep them sufficiently isolated from their environment, which is needed in order to maintain their superposition state, right? How do we do that? Well, we're going to need some kind of fancy error correcting codes to do that, right? And then, there are theoretical questions there as well about how do you design those error correcting codes, right? But there's also practical questions. How do you engineer a system, where the error rates are low enough that these codes can even be used at all, that they won't, that if you try to apply them, you won't simply be creating even more error than you're fixing. And what should be the physical basis for qubits? Should it be superconducting coils? Should it be ions trapped in a magnetic field? Should it be photons? Should it be some new topological state of matter? Actually, all four of those proposals and many others are all being pursued right now. So I would say that until quite recently in the field, like 5 years ago or so, the theoretical and the practical branches were pretty disjoint from each other, right? They were never enemies, so to speak. I mean, we might poke fun at each other, sometimes, but we were never enemies. I mean, the field always sort of rose or fall, as a whole, and we all knew that. But we just didn't have a whole lot to scientifically to say to each other, because the experimentalists were just trying to get 1 or 2 qubits to work well, right? And they couldn't even do that that much. And we theorists were thinking about, well, suppose you've got 1 billion qubits, or some arbitrary number. What could you do? And even what would still be hard to do even then? Right, a lot of my work has actually been about the limitations of quantum computers. But I also like to say the study of what you can't do, even with computers that you don't have. And only recently, the experimentalists have finally gotten the qubits to work pretty well in isolation, so that now it finally makes sense to start to scale things up. Not yet to 1 million qubits, but maybe to 50 qubits, maybe to 60, maybe to 100. This, as it happens, is what Google and IBM and Intel and a bunch of startup companies are trying to do right now. And some of them are hoping to have devices within the next year or two. That might or might not do anything useful, but if all goes well, we hope we'll at least be able to do something interesting, in the sense of something that would be challenging for a classical computer to simulate, and that at least proves the point that we can do something this way that is beyond what classical computers can do. And so as a result, even the most nitty-gritty experimentalists are now actually talking to us theorists, because now they need to know, not just as a matter of intellectual curiosity, but as a fairly pressing practical matter. Well, once we get 50 or 100 qubits working, what do we do with them? What do we do with them, first of all, that is hard to simulate classically? How sure are you that there's no fast classical method to do the same thing? How do we verify that we've really done it? And is it useful for anything, right? And and ideally, they would like us to come up with proposals that actually fit the constraints of the hardware that they're building, right? Where you could say, eventually none of this should matter, right? Eventually, a quantum programmer should be able to pay as little attention to the hardware as a classical programmer has to worry about the details of the transistors today, right? But in the near future, when we only have 50 or 100 qubits, each and every, you're going to have to make the maximum use of each and every qubit that you've got. And the actual details of the hardware are going to matter. And the result is that even, we theorists have had to learn about these details, in a way that we didn't before. And so there's been a sort of coming together of the theory and practical branches of the field just in the last few years that, to me, has been pretty exciting.
So you think similar to the way that functional programming, where everything was wrapped up in modules and things that people could poke and call and things, will happen for quantum computing in the near future?
Well, so there actually has been a fair amount of work on the design of quantum programming languages. There's actually a bunch of them out there now that you can download and try out if you'd like. There's one called Quipper. There's another one called Q# from Microsoft. There's, and there are several others. Of course, we don't yet have very good hardware to run the programs on yet. Mostly you can just run them in classical simulation, which, naturally only works well for up to about 30 or 40 qubits, and then it becomes too slow. But you can, if you would like to get some experience with quantum programming, you can try these things out today, and many of them do try to provide higher level functionalities, so that you're not just doing the quantum analog of assembly language programming, right? But you can think in higher level modules, or you can program functionally. I would say that in quantum algorithms, mostly we've just been doing theory and we haven't been implementing anything, but we have had to learn to think that way, right? If we had to think in terms of each individual qubit and each individual operation on 1 or 2 qubits, well, we would never get very far, right? And so we have to think in higher level terms, like there are certain modules that we know can be done. Like one of them is called the quantum Fourier transform, and that's actually the heart of Shor's famous algorithm for factoring numbers. It has other applications as well. Another one is called amplitude amplification. That's the heart of Grover's famous algorithm for searching long lists of numbers in about the square root of the number of steps that you would need classically. And that's also like a quantum algorithm design primitive that we can just kind of plug in as a black box, and it has many applications. So we do think in these higher level terms, but there's a different set of higher level abstractions than there would be for classical computing, and so you have to you have to learn those. But the basic idea of decomposing a complicated problem by breaking it down into its subcomponents, that's exactly the same in quantum computing as it is in classical computing.
Are you optimistic with regard to quantum computing in the medium to short term?
Well, it depends what you're asking. Am I optimistic about? So I am. I feel like the field has made amazing progress, both on the theory side and on the experimental side. Like we're not there yet, but we know a lot more than we did a decade ago, right? We've, some of what were my favorite open problems as a theorist, a decade ago have now been resolved. Some of them within the last year, actually. And the hardware, the qubits are not yet good enough to build a scalable quantum computer, right? In that sense, the skeptics can, legitimately say, well, we're not there yet. Well, no, duh, we're not. Okay, but if you look at the coherence times of the qubits, you look at what you can do with them, and you compare that to where they were 10 years ago or 20 years ago, there's been orders of magnitude type of progress, right? So the analogy that I like to make, Charles Babbage laid down the basic principles of classical computing in the 1820s, right? I mean, not with as much mathematical rigor as Turing would do later, but the basic ideas were there. He had what today we would call a design for a universal computer. So now imagine someone then saying, well, so when is this analytical engine going to get built? Will it be in the 1830s, or will it take all the way until the 1840s, right? Well, in this case, it took more than 100 years for a technology to be invented, namely the transistor, that really, fully realized Babbage's vision, right? I mean, the vacuum tube came along earlier, and you could say partially realized it, but, it was just not reliable enough to, to really be scalable in the way that the transistor was. And, we are now in the optimistically, we're in the very, very early vacuum tube era of quantum computing, okay? We don't yet have the quantum computing analog of the transistor. Because people don't even agree about which technology is the right one to scale up yet. Is it superconducting? Is it trapped ion? Is it photonics? Is it topological matter, right? So they're pursuing all these different approaches in parallel. The partisans of each approach have what sound like compelling arguments why none of the other approaches could possibly scale. I hope that they're not all correct, but people are still just, they've only just recently gotten to the stage where 1 or 2 qubits work well in isolation, and where it makes sense to try to scale up to 50 or 100 of them and see if you can get them working well together, at that kind of scale. And so I think the big thing to watch for in the next 5 to 10 years is what's been saddled with the somewhat unfortunate name of quantum supremacy. And this was coined before Trump, I hasten to say. But so this is just a term to refer to doing something with a quantum computer that's not necessarily useful, but that at least is classically hard. So that, as I was saying earlier, proves the point that you can do something that would take a lot longer to simulate it with a classical computer. And, this is the thing that Google and some others are going to take their best shot at within the next couple of years. What's what puts that in the realm of possibility is that, just a mere 50 or 100 qubits, if they work well enough, should already be enough to get us this, right? And, you in principle, you may be able to do this without needing error correction. Once you need error correction, then that enormously multiplies the resources that you need, right? To do even the simplest, what's called fault-tolerant computing might take many thousands of physical qubits, okay? Even though, everyone agrees that ultimately, if you want to scale to, to realize the true promise of quantum computing, or let's say to threaten our existing methods of cryptography, then you're going to need this fault tolerance. But that I expect we're not going to see in the next 5 to 10 years. If we do see it, that will be a huge shock. It'll be, as big a shock as it would be if you told someone in 1939 that, there was going to be a nuclear weapon in 6 years. Okay, in that case, there was a world war that sort of accelerated the timeline, you could say, from what it would otherwise be. In this case, I hope there won't be a world war that accelerates this timeline. But my guess would be that, if all goes well, then quantum supremacy might be achievable within the next decade. And I hope that after that, we could start to see some initial applications of quantum computing, which will probably be some very, very specialized ones. Some things that we can already get with, 100 or so non-error corrected qubits. Okay, and, by necessity, these are going to be very special things. They might mostly be physics simulations, or simulations of some simple chemistry problems. I actually have a proposed application for near-term quantum computers, which is to generate cryptographically secure random numbers. Those random numbers that you could prove to a skeptic really were generated randomly. Turns out that even like a 50 or 60 qubit quantum computer should already be enough to give us that. But the true, scalable quantum computing, the kind that could threaten cryptography and that could also speed up, optimization problems and things like that, that will probably require error correction. And, I could be pleasantly surprised. I'm not optimistic about that part becoming real in the next 5 to 10 years, but, since everyone likes an optimist, I guess I'll, I try to be optimistic that we will, take big steps in that direction and maybe even get there within my lifetime.